And now in this lecture we'll answer on two questions. In the first question we find out the size of this angle, angle x, or angle PQB is equals to x. In the second question we find out the area of this green shape. So we start with the first question. In the drawing we have a quarter circle, AOB is a quarter circle, therefore this angle AOB is equal to 90 degrees in size. In addition, we know that angle APQ is also a right angle, and we also know that AP equals to PQ, and our task is to find out the size of angle PQB is equal to x. We have to find out the value of x. So first of all, we complete the quarter circle to a semicircle. And define this point as M. So here we completed the quarter circle to a semicircle, and therefore AM is the diameter of the quarter of the semicircle according to our construction. Again, AM is the diameter of the semicircle according to our construction. AM is the diameter, it is absolutely a straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AM at point O? We have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will extend 97 PQ by a straight line until it touches the semicircle. But the question is where the extended 97 PQ will touch the semicircle. We will assume that the extended 97 PQ will touch the semicircle at this point. We define the touching point as point L. So actually we have peripheral angle APL that is equals to 90 degrees in size, and peripheral angle APL subtend on AL. Well, of course the extended 97 PQ touches the semicircle at point N, therefore peripheral angle APL subtend on AL. But it actually contradicts to rule 5. AL is definitely not the diameter of the semicircle because it doesn't pass through point O. So we have peripheral angle APL that is equal to 90 degrees in size, and still it doesn't pass, it doesn't subtend on the diameter of the semicircle because AL is definitely not the diameter of the semicircle. Why? Because it doesn't pass through point O. So it is a contradiction to rule 5. So if we click on rule 5, according to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. So we have, this is a circle, and this is peripheral angle AOB that is equal to 90 degrees in its size. Therefore, peripheral angle AOB must subtend on AEB, that is the diameter of the circle. So any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. AEB is the diameter of the circle. So here we have peripheral angle APL that is equal to 90 degrees in its size, and therefore, according to rule 5, it must subtend on the diameter of the circle. But actually it is subtend on AL, and AL is definitely not the diameter of the semicircle. So it is contradiction to rule 5. That is to say, the extended side PQ cannot touch the circle at point L, because then we will have contradiction to rule 5. We assume that the extended side PQ will touch the semicircle, will touch the circle at this point edge. So we have peripheral angle APH that is equal to 90 degrees inside according to what is given as the question, and peripheral angle APH subtend on AH. Still, we have the same contradiction to rule 5. We have the same contradiction to rule 5. Why? Because peripheral angle APH is equal to 90 degrees in its size, and therefore it must subset on the diameter of the semicircle. But peripheral angle APH subset on AH, and AH is definitely not the diameter of the semicircle, because AH doesn't pass from point O, that is the center of the semicircle. And we know that any diameter of the circle must pass from the center of the circle. AH doesn't pass from point O, therefore AH is not the diameter of the semicircle, therefore it is contradiction to rule 5. Because peripheral angle APH must subtend on the diameter of the semicircle, and AH is definitely not the diameter of the semicircle, therefore we have contradiction to rule 5. Due to those two contradictions, we must conclude that the extended side PQ will touch the semicircle at point M and not in any other point. In this way, we will not have contradiction to rule 5 anymore. Why? Because now we have peripheral angle APM that is equal to 90 degrees in its size according to what is given as the question, and it's subset on AM. AM is the diameter of the semicircle, exactly according to rule 5. Peripheral angle APM equals to 90 degrees in its size, and it's subset on the diameter of the semicircle AM, exactly according to rule 5. In the next step, we join points A and Q together by a straight line. By joining points A and Q, we get that the right and associated triangle, triangle APQ. Triangle APQ is a right angle because angle APQ is right angle. Triangle APQ is also an associated triangle because side AP equals to side PQ. And we have the rule that in front of equal sides in the triangle there are equal angles. So if we relate to the right and associated triangle, triangle APQ, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. You also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and therefore it is true in triangle APQ. The sum of the angles in triangle APQ must be equal to 180 degrees. So which angles we have in the right triangle, triangle APQ? We have this angle, this is the right angle, this is to say it is equal to 90 degrees in size. plus alpha, that is plus 2 alpha. In total, the sum of those triangles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally get that alpha equals to 90 degrees over 2 is 45 degrees. So the size of this missing angle is alpha equals to 45 degrees. And this is also angle alpha that is equals to 45 degrees in its size. In the next step, we'll prove that those two right angles can go into each other according to side angle side rule. That is to say, we'll prove that the right upper triangle AQO can go into the right lower triangle OQM according to side angle side rule. You know that AO is the radius of the semicircle, so we define the radius of the semicircle as R. OM is also the radius of the semicircle, that is equal to R according to our definition. So what those two right angles are similar to each other. So we prove that the right upper triangle AOQ can go into the right lower triangle OQM. So why those two right triangles can go into each other? First of all, side AO of the right triangle AQO is equal to side OM of the right triangle OQM. The above they are the semicircle, therefore they are equal to each other. So AO equals to OM. The above they are the semicircle, that is equal to R according to our definition, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So angle AOQ with the right triangle AOQ is equal to angle MOQ with the right triangle QOM. And again, I should found out that angle AOQ with the right triangle AOQ is equal to angle MOQ with the right triangle OQM. They are both equal to 90 degrees and therefore they are equal to each other. And finally, side OQ is a common side that belongs to both triangles. So we can write down that OQ equals to itself. It's a common angle that belongs to both triangles. And again, OQ equals to itself is a common angle that belongs to both triangles. So I can prove that those two right triangles can go into each other according to side angle side rule. That is to say, we should prove that the upper right triangle AOQ can go into the lower right triangle OQM according to side angle side rule. That is to say, we should prove that those two sides and the angle that is included between those two sides of the right triangle AOQ are corresponding equal to those two sides and the angle that is included between those two sides in the right triangle OQM. And therefore those two right triangles can go into each other according to side angle side rule. So right now, we have found out that the upper right triangle AOQ congruent, this is the sign of congruent, to the lower right triangle OQM according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive the side AQ, the side AQ of the right triangle AOQ is equal to side QM of the right triangle OQM. So AQ equals to QM. Repeat again, from the fact that those two right triangles can go into each other, we derive that side AQ of the right triangle AOQ is equal to side QM of the right triangle OQM according to the rule that says that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. So we found out that AQ equals to QM. So we focus on the big triangle AQM. We have the rule that in front of equal sides in the triangle there are equal angles. So if we relate to the big triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other. Okay? So in the next step, I will present to you a new rule, rule 8, and we will implement the new rule in our drawing. According to rule 8, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. So in the drawing we have triangle ABC that could be any triangle. Those three angles alpha, beta, and gamma are defined as an interangles because they are located inside triangle ABC. While this is angle ACB, ACF, that is equal to angle E. Angle E is defined as an external angle of triangle ABC because of the fact that it is located outside triangle ABC. And according to this rule 8, the size of an external angle ACF that is equal to E is equal to the sum of the two interangles that are not adjacent to it. This is the internal angle gamma that is definitely adjacent to angle E. The two other interangles that are not adjacent to angle E are alpha and beta. Therefore, according to this rule 8, the sum of the two interangles that are not adjacent to angle E is actually alpha plus beta, that is equal to angle E. So the size of the external angle E is equal to alpha plus beta, that is the sum of the two interangles that are not adjacent to angle E. So we can implement rule 8 in our drawing. So in our drawing, if we relate to the big triangle AQM, this is angle AQB that is defined as an external angle in relation to triangle AQM because angle AQM, why it is an external angle? Because angle AQM is not located inside triangle AQM, but it is located outside triangle AQM. So the size of the external angle AQM, according to rule 8, must be equal to the sum of the two triangles that are not adjacent to it. This is angle AQM that is definitely adjacent to this angle AQP. The two other angles in triangle AQM that are not adjacent to angle AQP are those two angles. This is to say beta and beta. So beta plus beta equals to the external angle AQP, according to rule 8. Repeat again, according to rule 8, the size of the external angle in relation to the big triangle AQM, the size of the external angle AQM is equal to the sum of the two triangles that are not adjacent to it. That is to say it is beta plus beta. Beta plus beta is 2 beta. So the size of the external angle AQM, of the big triangle AQM, the size of the external angle AQM is equal to 2 beta. Actually, the external angle is angle AQP. So the size of the external angle AQP in relation to the big triangle AQM, the size of the external angle AQP is equal to beta plus beta, that is 2 beta. Repeat again, the size of the external angle AQP in relation to the big triangle AQM is equal to beta plus beta, that is actually the sum of the two triangles that are not adjacent to angle AQP. So the size of the external angle AQP is equal to 2 beta. But we have already found out that the external angle AQP is equal to 45 degrees in size. So we can substitute angle AQP by 45. So 45 degrees is equal to 2 beta. Here we divide this equation by 2 and finally get that the missing angle beta is equal to 45 degrees over 2, that is 22.5 degrees. So the missing side beta, the missing angle beta is equal to 22.5 degrees in its size. Actually, this is the missing angle beta, that is equal to 22.5 degrees in its size. And this is also angle beta, that is equal to 22.5 degrees in its size. We also know that the sum of the angles in the triangle is equal to 180 degrees. So if you relate to the right triangle QOM, the sum of the angles in the right triangle OQM must be equal to 180 degrees. So which angles we have in the right triangle OQM? We have this angle that is equal to 90 degrees. Plus this angle beta that is equal to 22.5 degrees. Plus this missing angle OQM. So in total, the sum of those two angles must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the triangles of the right triangle OQM, that is 90 degrees plus 22.5 degrees plus the missing angle OQM, in total they must be equal to 180 degrees. Here we subtract 90 degrees from the equation and we get that 180 degrees minus 90 degrees is 90 degrees is equal to 22.5 degrees plus the size of this missing angle OQM, which again 22.5 degrees plus the size of the missing angle OQM, in total they must be equal to 90 degrees. Here we subtract 22.5 degrees from this equation and we get that the size of the missing angle OQM is equal to 90 degrees minus 22.5 degrees, it is equal to 67.5 degrees in its size. So here, this is the missing OQM, that is equal to 67.5 degrees in its size. We have the rule that vertex angles are equal to each other. Those two angles are defined as vertex angles and they are equal to each other. That is to say, angle alpha equals to angle beta. Likewise, those two angles 1 and 2 are also defined as vertex angles and therefore they are equal to each other. That is to say, angle 1 equals to angle 2. So we can implement the rule in our drawing. One put in our drawing. Those two angles are defined as vertex angles and therefore they must be equal to each other in their sizes. That is to say, angle x equals to 67.5 degrees. According to the rule that says that vertex angles are equal to each other in their sizes, we get that angle x equals to 67.5 degrees in its size. So the answer to the question is the size of the angle that we are looking for in this question, that is actually angle x, is equals to 67.5 degrees in its size. So we finish with the first question. In the next step, we'll present you the second question and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have a semicircle. It is given us the question that PQ equals to 10 units in its length. That is to say, the diameter of this semicircle equals to 5. Therefore, the radius must be equal to 10 over 2, that is 5. So the radius of this semicircle equals to 5 units in its length. in the domain we have a semicircle, PQ equals to 10. In addition, we know that inside this semicircle we have the big square ABCD and the small square MECF. Again, our task is to find out they have this ring shape. So first of all, we define the center of this semicircle. This point is point O. We join points O and A together by a straight line. Point A is the center of the semicircle. Point O is the center of the semicircle. Point A is the point on the semicircle itself. Therefore, OA is the radius of this semicircle. This is equal to 5 units in its length. Likewise, we join points O and E together by a straight line. OE is, of course, the radius of the semicircle. This is equal to 5 units in its length. In the next step, we define one side of square ABCD as A. Therefore, AB equals to BC equals to CD equals to DA equals to A. We define the length of this small line segment OC as X. So what is the length of OB? What is the length of OB? OB equals to BC minus OC. Again, OB equals to BC minus OC. So already know. OB equals to BC minus OC. So OB in total equals to BC, that is A, according to our definition, minus OC, that is X. So in total, OB equals to A minus X units in its length. OB equals to A minus X units in its length. In the next step, we define one side of the small square MEFC as B. So EF equals to B, CF also equals to B, CM equals to B, and ME also equals to B. So MEFC is a square, and we know that all the angles in any square are right angles. Therefore, this angle is a right angle. Likewise, ABCD is also a square, so this angle must be also equal to 90 degrees in its size. So in the next step, I copy those two right angles in a new page and we implement the Pythagoras theorem on those two right angles. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So copy the right angle ABO in a new page and we implement on it the Pythagoras theorem. Here by PT is abbreviation for Pythagoras theorem. Size BO of the right angle ABO equals to A minus X units in its length. The hypotenuse AO equals to 5 units, it is the radius of the semicircle, and AB equals to A units in its length according to our definition. It is one side of square ABCD. Okay. This is the right angle ABO that is coming from the original domain. In this right angle ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So write it down, this will be equation 1. AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. The hypotenuse AO equals to 5 units in its length, therefore AO squared is 5 squared, that is 25, and this equals to AB squared. AB is A, therefore AB squared is A squared plus BO squared. BO is A minus X, therefore BO squared is equal to A minus X squared. So in total, according to equation 1, we shall find out that 25 equals to A squared plus A minus X squared. In the next step, I'll copy this right angle OEF in a new page and Can you prevent the Pythagoras theorem on this right triangle or EF? EF by PT is the equation for Pythagoras theorem. This is the right triangle OEF, this is a copy from the original drawing. According to the Pythagoras theorem, in this right triangle OFE, OF squared, that is the square of the hypotenuse, equals to FE squared plus EO squared. So write it down. OF squared, that is the square of the hypotenuse, is equal to FE squared plus OE squared. OF is 5, therefore OF squared is 5 squared, that is 25. And it is equal to FE squared. FE is B, therefore FE squared is B squared plus OE squared. OE equals to X plus B, therefore OE squared is X plus B squared. So in total, according to equation 2, we have found out that 25 equals to B squared plus X plus B. Well, according to equation 1, we already found out that 25 equals to A squared plus A minus X squared. In the next step, we get the equation 3 that says that 25 according to equation 1 must be equal to 25 according to equation 2. And again, according to equation 3, according to equation 1 must be equal to 25 according to equation 2. So 25 according to equation 1 equals to A squared plus A minus X squared. And it must be equal to 25 according to equation 2. 25 according to equation 2 is equal to B squared plus X plus B squared. So in total, according to equation 3, we should find out that A squared plus A minus X squared equals to B squared plus X plus B squared. Here we'll open the brackets on both sides of this equation, equation 3, and we get that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared plus 2 times A times X. And it is equals to B squared plus X plus B squared. So it is B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. So here we have X squared on both sides of this equation, 3, so X squared gets cancelled. After I cancelled X squared, in this side of equation 3 we left with A squared plus A squared, that is 2A squared, plus 2 minus 2AX, equals to B squared plus B squared is 2B squared plus 2xb. So in total, according to equation 3, we should find out that 2a squared minus 2ax equals to 2b squared plus 2xb. Here we add 2ax to this equation, equation 3. And you get that according to equation 3, 2 times a squared equals to 2ax plus 2bx plus 2b squared. So according to equation 3, I should find out that 2a squared equals to 2ax plus 2bx plus 2b squared. Here we subtract 2b squared from this equation, equation 3. And we get that according to equation 3, 2a squared minus 2b squared equals to 2ax plus 2bx. So here we divide this equation 3 by 2 and finally get that according to equation 3, 2a squared minus 2 is a squared minus 2b squared over 2 is minus b squared equals to 2ax over 2 is ax plus 2bx over 2 is bx. So to now according to equation 3, we have found out that a squared minus b squared equals to ax plus bx. So we have the famous algebraic identity that says that a squared minus b squared equals to a plus b times a minus b. And it is equals to ax plus bx. So here we take x as a common factor from those two expressions. So inside the brackets, we left only with a plus b. A is the left of one side of square ABCD, and b is the left of one side of the small square MEFC. Therefore, a plus b must be a positive number, because if you add two positive numbers, the result must be a positive number. So here, therefore, because of the fact that a plus b must be a positive number, it can never be equal to 0. Therefore, it is allowable to divide this equation 3 by a plus b. So we divide this equation by a plus b, and we get that according to equation 3, we have a plus b that we get cancelled, and we have to only with a minus b this side of equation 3, this is equals to a plus b also will get cancelled, and we have to only with x. So total according to equation 3, we actually found out that a minus b equals to x. According to equation 3, a minus b equals to x. So here we add b to this equation, equation 3, and finally we get that a equals to x plus b. So here we subtract x from this equation, equation 3, and finally get that according to equation 3, a minus x equals to b. If a minus x equals to b, we square on this equation 3, and we get that a minus x squared equals to b squared. Again, according to equation 3, we have found out that a minus x squared equals to b squared. Our task is to find out the area of this given shape. So what is the area of the given shape? From the domain, it is very easy to see that the area of the given shape in total is equal to the area of the semicircle minus the area of the big square ABCD minus the area of the small square MEFC. So if it again, we should find out that the area of the green shape in total is equal to the area of the semicircle minus the area of the big square minus the area of the small square. So what is the area of the semicircle? Actually, you know that the area of any semicircle equals to the area of the circle over 2. That is to say, it is pi r square over 2. But we already found out that the radius of this semicircle r equals to 5. Therefore, r squared is 5 squared, that is 25. So pi r squared over 2 is 25 pi over 2. So the area of this semicircle equals to 25 pi over 2 square units in its size, minus the area of this big square. Now, we know that one side of this square is a, therefore the area must be equal to a square. So the area of the big square is equal to a square, so it is minus the area of the big circle, that is equal to a square, so it is minus a square, minus the area of the small circle. One side of the small circle, the small square equals to b. Therefore, the area of the small square must be equal to b square. So in total, if we found out that the area of the green shape equals to the area of the semicircle, that is 25 pi over 2, minus the area of the big square, that is a square, minus the area of the small square, that is minus b square. So the area of the green shape in total equals to 25 pi over 2. Here we take minus 1 as a common factor from those two expressions. So inside the brackets we have a square plus b square. So in total we found out that the area of the green shape equals to 25 pi over 2 minus a square plus b square. But according to equation 1, we have already found out that (25) equals to a square plus a minus x square. Again, according to equation 1, we have already found out that 25 equals to a square plus a minus x square. So 25 equals to a square plus a minus x square. But we already found out that a minus x square equals to b square. So we can substitute a minus x square in this equation 1 by b square. So in total we found out that a square plus b square equals to 25. Again, we found out that a square plus b square equals to 25. And therefore, the area of the green shape in total equals to 25 pi over 2 minus a square plus b square. But a square plus b square equals to 25, so we substitute a square plus b square by 25. So in total, we found out that the area of the green shape equals to either 25 pi over 2 minus 25 square units. On terms of numbers, the area of this, the value of this expression is equal to 14.27 square units in its size. And again, we found out that the area of this green shape, it is equal to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the area of this green shape is equal to 14.27 square units in its size. So we finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our task was to find out the size of this angle, angle x, so angle p cubit is equal to x. We have to find out the value of x, the value of angle x. So in the domain, we have a quarter circle, AOB is a quarter circle, therefore this angle AOB is equal to 90 degrees in size. It is so in any quarter circle actually. In addition, inside this quarter circle AOB, we have this angle APQ. This is also a right angle. And we also know that AP equals to PQ. Again, our test is to find out the size of angle PQV that is equal to x. We have to find out the value of x. So in the first step, we completed this quarter circle to a semicircle. And therefore, AM must be equal to the diameter of the semicircle according to our construction. So again, AM is the diameter of the semicircle according to our construction. Because we completed the quarter circle to a semicircle. So AM is the diameter of the semicircle. So AM is the diameter, it is absolute straight line. So if you focus on the right side of the straight line AM at point O, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of AM at point O, we have this angle that is a right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in size. In the next step, we extended line segment PQ by straight line. But the question is, well, the extended line segment PQ will touch the semicircle. We'll assume that the extended line segment PQ will touch the semicircle at this point L. And now, therefore, we'll have peripheral angle APL that is equal to 90 degrees in size, and it's subtend on AL. But AL is definitely not the diameter of the semicircle because it doesn't pass from point O, that is the center of the semicircle. We know that any diameter must pass from the center of the semicircle. Therefore, AL is definitely not the diameter of the semicircle. So we have a contradiction to all five because we have peripheral angle APL that is equal to 90 degrees in size, and it must subtend on the diameter of the semicircle. But it's subtend on AL, and AL is definitely not the diameter of the semicircle. So we have a contradiction to all five, and due to the contradiction to all five, we will cancel this possibility. That is to say, the extended side PQ will not touch the semicircle at this point L. Now we assume that the extended side PQ will touch the semicircle at this point H. So again, we have contradiction to all five because we have peripheral angle APH that is equal to 90 degrees in size, and therefore it must subtend on the diameter of the semicircle. But it is actually subtend on AH, and AH is definitely not the diameter of the semicircle. Why? Because AH doesn't pass from point O, that is the center of the semicircle. Therefore, AH doesn't pass from point O, therefore it is not the diameter of the semicircle. So we have peripheral angle that is equal to 90 degrees in size, and the C doesn't subtend on the diameter of the semicircle because AH is definitely not the diameter of the semicircle. So due to the contradiction to all five, we'll have to conclude that the extended side PQ must touch the circle at point M and not in any other point. Now we will not have any contradiction to all five because we have peripheral angle APM that is equal to 90 degrees in size, and indeed it's subtend on AM that is the diameter of the semicircle exactly according to all five. Okay, so in the next step we join points A and Q together by straight line. By joining points A and Q, we created the right and associated triangle APQ. So in relation to triangle APQ, we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those, we know that AP equals to PQ. So in front of those two equal sides in the triangle APQ, we have those two angles that must be also equal to each other and their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, therefore it is true in triangle APQ. So these angles we have in that in associated triangle APQ, we have this angle that is 90 degrees, plus alpha, that is plus 2 alpha, in total they must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. Here we divided this equation by 2 and found out that the missing angle alpha equals to 90 degrees over 2, that is 45 degrees. So this is the missing angle alpha that equals to 45 degrees in size, and this is also the missing angle alpha that equals to 45 degrees in size. In the next step, it proves that those two right triangles can go into each other according to side angle side rule. That is to say, we prove that the upper right triangle AQO can go into the lower right triangle OQM according to side angle side rule. So, why those two triangles can go into each other? First of all, AO equals to OM, they are both the radii of the same circle, therefore they are equal to each other. AO equals to OM equals to R. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, side OQ is a common side that belongs to both triangles. So side OQ equals to itself is a common side that belongs to both triangles. So I shall prove that those two triangles can go into each other according to side angle side rule. That is to say, we shall prove that those two sides and the angle that is included between those two sides in the right triangle AOQ are corresponding equal to those two sides and the angle that is included between those two sides in the right lower triangle OQM. And therefore those two right triangles can go into each other according to side angle side rule. So if again, if you found out that the upper right triangle AOQ congruent, this is the sign of congruent to the right lower triangle OQM according to side angle side rule. And from the fact that those two triangles can go into each other, we have that side AQ of the right triangle AOQ is equal to side QM of the right triangle OQM. We have that AQ equals to QM. AQ equals to QM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say AQ and QM, must be also equal to each other in their lengths. So AQ equals to QM. So if we relate to the big triangle AQM, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. So in the next step, I presented to you a new rule, that is rule 8, and we implemented rule 8 in our drawing. So I repeat quickly on rule 8. According to rule 8, an external angle of a triangle is equal to the sum of the two interangles that are not adjacent to it. So in the dominant triangle ABC, that could be any triangle. Those triangles alpha, beta, and gamma are defined as an interangles of triangle ABC because of the fact that they are located inside triangle ABC. While this is angle ACF, this is equals to E. Angle ACF is defined as an external because it is located outside triangle ABC. And according to this rule, rule 8, the size of the external ACF is equal to E. It is equal to the sum of the two interangles that are not adjacent to it. This is the angle gamma is definitely adjacent to angle E. The two other angles that are not adjacent to angle E are those two angles alpha and beta. And the sum of them is alpha plus beta. So alpha plus beta equals to the size of the external angle ECF. So E equals to alpha plus beta, according to rule 8. So we can actually implement the new rule 8 in our drawing. While in our drawing, if we focus on the big triangle AQM, this is an angle AQP that is defined as an external angle to triangle AQM. The size of the external angle AQP must be equal to the sum of the two triangles that are not adjacent to it. This triangle definitely adjacent to angle AQP. The two other angles that are not adjacent to angle E are those two angles, beta and beta. Therefore, the size of the external angle AQP equals to beta plus beta according to rule 8. So again, in relation to the big triangle AQM, the size of the external angle AQP equals to beta plus beta, that is 2 beta. So the size of the external angle AQP is 2 beta. But we already found out that the size of the external AQP is 45 degrees. Therefore, we can substitute angle AQP by 45 degrees, and again that 45 degrees equals to 2 beta. Here we divided the equation by 2 and finally found out that the size of angle beta is 45 degrees over 2, that is 22.5 degrees. So this is angle beta, that is equal to 22.5 degrees in its size, and this is also angle beta, that is equal to 22.5 degrees in its size. In the next step, we focus on the right triangle OQM. On the right triangle OQM, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have on the right triangle OQM, we have this angle that is a right angle, plus this angle that is equal to 22.5 degrees, that is actually angle beta, plus this missing angle, angle OQM, and total the sum of those three angles must be equal to 180 degrees. And again, in the right triangle OQM, the sum of three angles of the right triangle OQM must be equal to 180 degrees. So 90 degrees plus 22.5 degrees plus the size of the missing angle OQM, in total the sum of those three angles must be equal to 180 degrees. Here we subtract the 90 degrees from this equation and find out that 180 degrees minus 20 degrees is 90 degrees. So 90 degrees equals to 22.5 degrees plus the size of the missing angle OQM. Here we subtract the 22.5 degrees from this equation and find out that the size of the missing angle OQM equals to 90 degrees minus 90 degrees minus 22.5 degrees. 90 degrees minus 22.5 degrees is equal to 67.5 degrees. So we should find out that the size of this missing angle OQM is equal to 67.5 degrees in size. We have the rule that says that vertex angles are equal to each other. Those two angles are defined as vertex angles and therefore they are equal to each other. That is to say alpha equals to beta. Those two angles are also defined as vertex angles and therefore they are equal to each other. That is to say angle 1 equals to angle 2 in its size. So we can actually implement the rule in our drawing. In our drawing we have those two vertex angles that are equal to each other. That is to say angle x equals to 67.5 degrees in size. And so then we found out that the angle that we are looking for in this question, that is angle x, is equal to 67.5 degrees in its size. The size of the angle x is equal to 67.5 degrees in its size. So we finish with the first question. In the next step I presented to you the second question and we solve the second question of this lecture. In the second question, our task is to find out the area of this ring shape. So in the drawing we have a semicircle. This is a semicircle, PQ equals to 10. That is to say the diameter of this semicircle equals to 10, therefore the radius must be equal to 5. We define the center of this semicircle, this point is point O. We join points O and A together by side line. Point O is the center of the semicircle, point A is the point of the semicircle itself, therefore OA is the radius of this semicircle, this is equal to 5. Likewise, we join points O and E together by side line. OE is also the radius of this semicircle, that is equal to 5 units in its length. In the next step we define, so inside this semicircle we have those two squares. We have the big square ABCD and the small square MEFC. We define the length of one side of square ABCD as A. So AB equals to BC equals to CD equals to DA equals to A. So we define this short line segment OC as X. So what is the length of BO? BO equals to BC minus OC. Again, BO equals to BC minus OC. So BO equals to BC, that is A, minus OC, that is X. So in total, BO equals to A minus X. BO equals to A minus X. We define one side of the small square MEFC as B. So EF equals to FC equals to CM equals to MF equals to B, according to our definition. The sum of the angles, therefore, all the angles inside the square are right angles, therefore this angle is a right angle. ABCD is also a square, therefore the size of this angle is equal to 90 degrees. So, in the next step, I complete the right triangle AOB in a new page, and we implemented the Pythagoras theorem in this right triangle AOB. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle APO that I got from the original domain. According to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is 5, therefore AO squared is 5 squared, that is 25, and it is equal to AB squared. AB is 8, therefore AB squared is A squared, plus BO squared. BO is A minus X, therefore BO squared is A minus X squared. So in total, according to the equation 1, we actually found out that 25 equals to A squared plus A minus X squared. In the next step, I complete the right triangle OEF in a new page, and we implemented the Pythagoras theorem on this right triangle OEF. So here, this is right triangle OEF that I copied from the original domain. According to the Pythagoras theorem, in this right triangle OEF, OF squared, that is the square of the hypotenuse, equals to FE squared plus EO squared. OF squared equals to FE squared plus OE squared. OF is 5, therefore OF squared is 5 squared, that is 25, and it is equal to EF squared. EF is B, therefore EF squared is B squared, plus OE squared. OE is X plus B, therefore OE squared is X plus B squared. So according to equation 2, we have found out that 25 equals to B squared plus X plus B squared. But according to equation 1, we have only found out that 25 equals to A squared plus A minus X squared. In the next step, we created equation 2 that said that 25 according to equation 1 must be equal to 25 according to equation 2. Again, 25 according to equation 1 must be equal to 25 according to equation 2. And then again, according to equation 3, 25 according to equation 1 must be equal to 25 according to equation 2. 25 according to equation 1 equals to A squared plus A minus X squared. And it must be equal to 25 according to equation 2. 25 according to equation 2 equals to B squared plus X plus B squared. So in total, according to equation 3, we have found out that A squared plus A minus X squared equals to B squared plus X plus B squared. Here we open the brackets of both sides of this equation, equation 3, and finally found out that according to equation 3, A squared plus A minus X squared. A minus X squared equals to A squared plus X squared minus 2 times A times X. In the other side of equation 3, we have B squared plus X plus B squared. X plus B squared equals to X squared plus B squared plus 2 times X times B. So here we have X squared on both sides of this equation 3, so X squared will get cancelled. After cancelled X squared, on this side of the equation 3, we left with A squared plus A squared, this is 2A squared, minus, again, 2A squared minus 2AX. So in this side of equation 3, we have 2A squared minus 2AX. And this is equals to B squared plus B squared, this is 2B squared, plus 2xb. So in total, according to equation 3, we actually found out that 2a squared minus 2ax equals to 2b squared plus 2xa. Here we added to this equation, equation 3, 2ax, and finally found out that according to equation 3, 2a squared equals to 2ax plus 2bx plus 2b squared. Here we divided this equation 3 by 2, and finally found out that according to equation 3, 2a squared over 2. Actually, here we added, we subtracted 2b squared from this equation 3. We found out actually that according to equation 3, 2a squared minus 2b squared equals to 2ax plus 2bx. Here we divided this equation 3 by 2, and finally found out that according to equation 3, 2a squared over 2 is a squared, 2b squared over 2 minus 2b squared over 2 is minus b squared, and this equals to 2ax over 2 is ax, and 2bx over 2 is bx. So in total, according to equation 3, we found out that a squared minus b squared equals to ax plus bx. We have the famous algebraic identity that states that a squared minus b squared equals to a plus b times a minus b. And it is equal to ax plus bx. Here we took out x as a common factor from those two expressions, so inside the brackets we left with a plus b. So in total, according to equation 3, we actually found out that a plus b times a minus b equals to x times a plus b. A and b are the lengths of the length of one side of a is the length of side of one side of square ABCD, and b the length of one side of square MEFC. And therefore, the positive numbers, when you add two positive numbers to each other, the result must be a positive number. Therefore, a plus b, it is a positive number, it can be equal to 0. For that reason, we can divide this equation 3 by a plus b. So we divide this equation 3 by a plus b. So here a plus b will get cancelled, and we left only with a minus b. Here a plus b also will get cancelled, and we left only with x. So in total, we should find out that a minus b equals to x. Here we added b to this equation, and finally found out that a equals to x plus b. Here we subtracted x from this equation, and finally found out that a minus x equals to b. So b equals to a minus x. If b equals to a minus x, we just square the two sides of this equation, and we get that a minus x squared equals to b squared. Again, a minus x squared equals to b squared. Our test is to find out the area of this green shape. What is the area of the green shape? From the drawings, it's very easy to see that the area of this green shape is equal to the area of the semicircle minus the area of the big square minus the area of the small square. Repeat again, the area of this green shape must be equal to the area of the big semicircle minus the area of the big square minus the area of the small square. Okay, again, the area of the green shape in total equals to the area of the semicircle minus the area of the big square minus the area of the small square. The area of any semicircle equals to the area of the circle over 2. That is to say, it is pi r square over 2. But r is 5, therefore r square is 5 squared, that is 25. So pi r square over 2 is 25 pi over 2. The area of this semicircle is 25 pi over 2. Minus the area of the big square, one side of this square, big square is a, therefore the area of this big square must be equal to a square. So it is minus a square. One side of this small square is b, therefore the area of this small square must be equal to b square. So it is minus b square. So in total we found out that the area of the green shape equals to pi r square, 25 pi over 2 minus a square minus b square. Here we took 1 minus 1 as a common factor from those two expressions, so inside the brackets we have a square plus b square. So in total we found out that the area of this green shape equals to 25 pi over 2 minus a square plus b square. But according to equation 1, we only found out that 25 equals to a square plus a minus x square. But we only found out that b equals to a minus x, therefore b square equals to a minus x square. So a minus x square equals to b square. According to equation 3, a minus x square equals to b square. Therefore, we can substitute a minus x square by b square. We did it, and we found out that 25 equals to a square plus b square. Again, according to equation 1, 25 equals to a square plus b square. So here, we can substitute a square plus b square by 25, because 25 equals to a square plus b square according to equation 1. We did it, and we found out that in total, the area of the green shape equals to 25 pi over 2 minus a square plus b square, that is 25. So in total we found out the area of the green shape, that is the area of this green shape, that is the area that we are looking for in this question, is equal to either 25 pi over 2 minus 25, or in terms of numbers, the value of this expression, 25 pi over 2 minus 25, is 14.27 square units in its size. So in total we found out the area of this green shape, that is the area that we are looking for in this equation, is equal to either 25 pi over 2 minus 25 square units in its size. In terms of numbers, the area of this green shape is equal to 14.27 square units in its size. Okay, thank you very much.